So let's look at computing Fibonacci numbers as an example. Of course, computing Fibonacci numbers has been done for centuries, and I'm sure if you go online you can find as many Fibonacci numbers as you want, but it's a good test case for comparing various methods, and it also takes me into the territory of dealing with round-off errors, which is something that we also discussed this week. So let's spend a little bit of time on that. So first, this is the basic definition of a Fibonacci sequence. This is essentially done as the definition. We say that Fibonacci number n is the sum of Fibonacci number n minus 1 plus Fibonacci number n minus 2. And then, of course, we need some base case. And the way this is done is that we say that Fibonacci number 0 is 0, Fibonacci number 1 is 1. And I've implemented this in a very primitive way by just saying that if n is less than or equal to 1, I return n. So this I've done, you can see directly, and I also do it with a remember table. And as we saw already when we introduced the remember tables some time ago now, this is a very good idea to have a remember table, because otherwise the time consumption will just grow exponentially, because whenever I call, I will issue two new computations of Fibonacci 0, and I keep on doing this and it piles up. But if I use option remember, I will reuse the values and it's not nearly as slow. There's another way of computing the Fibonacci numbers, because we also know that there's a closed form for them. And this closed form you can get by looking at the generating function for the Fibonacci numbers that we actually determined earlier in the course. But the formula, sometimes called Binet's formula, you take these two numbers related to the golden mean, and you take their nth powers, subtract them and divide by the square root of 5, and then you get an integer out, which is actually exactly the Fibonacci number. This works for any n, but then you can see that if n gets big, because this number is somewhere between minus 1 and 0, its nth powers will go to 0, whereas this number is somewhere between 1 and 2, its nth powers will go to infinity. So what you can do is you can simply forget this term and then round off to the nearest integer, knowing that the result of the complicated expression here is in fact an integer. And this works even from the very beginning. So what you can simply do is you round off, or what I'm doing here, I'm adding a half and I round down. So these are the four Fibonacci sequence generators that I start looking at. And as we will see, they are very different in terms of efficiency. And in order to deal with this in a practical way, I've invented a little program called f-timing. So what f-timing does is that it uses a command in Maple called time limit. The way that time limit works is that it will run a certain procedure, but not for longer than a certain given amount of time. I will give it 10 seconds. So what happens is that if Maple detects that the computation takes more than 10 seconds, it will give up and stop the computation. And then in order to generate some data, I look at the Fibonacci numbers of the powers of 2. So I start by looking at the Fibonacci number 2, then number 4, number 8, and 16, and so on. And I will simply see how far I can get before spending 10 seconds on one of these individual computations. So maybe let's spend a little bit of time on this construction here, because this is a little bit more advanced than the things that we've discussed this far. So there's a try end try clause, which is something that you do if you're asking Maple to do something that you think may result in an error. So if you think that perhaps you're going to divide by 0 or something nasty like that, what you can do is you can put a try end try around, and then what happens is that if an error is issued in this try end try block, you can catch that error, and then sort of, instead of going to an error message directly to the user, you can catch the error and decide to do something else. And then what I'm deciding to do here is that if there is an error, and the error will happen when the computation takes more than 10 seconds, then I will catch it. That means that there's no error message sent to the user, and then I will break out of the do and do loop and just return. Right? So the program simply works by saying, I will now compute as many Fibonacci numbers at powers of 2 that I can do before spending more than 10 seconds, and then I will compile all the information in L and return that to the user. And the information I need is the time, but you can see I cannot use time directly as I did before on the Fibonacci computation, because that's sort of packaged inside the time limit thing. So what I do instead is that I use time with an empty input. What that does is that it records a timestamp, so it simply keeps track of what the time was when I started my computation, and then I just take the timestamp when I end the computation and subtract the other timestamp. So that's another way of timing something. This is always done in seconds in Maple. So if I run f timing with Fibonacci 0, which is the first and primitive command that I defined, you'll see I'm going to have to wait because I'm waiting for my program to spend more than 10 seconds. And you can see this will happen already at 2 to the 6, which is 64. So Fibonacci 0 cannot even compute the 64th Fibonacci number. So that's not very impressive. And for the 2 to the 5, which is 32, that took 4.5 seconds. So these numbers, by the way, are just the numbers. I'm just taking the last 7 digits of the numbers that I computed just to make sure that they're correct. Okay, so so what this does is that it shows us that not having a remember table is a really bad idea. You can only get to 32 before going beyond 10 seconds. So when you use it with a remember table, you'll see that actually you run into a problem here. And running into a problem in this setting is actually good news, because it means that before spending 10 seconds, Maple can compute a lot of Fibonacci numbers. But the thing is that when what's going on here is that suppose I just forget Fibonacci 1, so I can show you what's going on here. So I forget Fibonacci 1, so that means I delete the remember table, and now if I run Fibonacci 1 on a small number like 30,000, you can see I get an error, right? And the reason why I get an error is that when Maple tries to compute the Fibonacci number, of course it has to call itself at 29,999 and 29,998, and then it sort of keeps on going for so long that the stack keeping track of the recursion gets filled. This happens already at 20,000, whereas you can do 10,000, which is a fairly big number. But what's interesting now is that now I can compute 20,000, because now the remember table has the information up to 10,000, so there's not so far down, and I can also compute to 30,000. These are enormous numbers that I don't really want to see, but you can see that this problem that I've encountered is a fairly easy fix for that, because I will just say that if you ask Fibonacci 1 to compute the Fibonacci number at a number bigger than, say, 10,000, I will just run it at n minus 10,000 in order to fill up the remember table so I don't run into this problem. So it's sort of, I take this big computation and I cut it down in little pieces in order not to overwhelm the size of the remember table. There's something weird going on here, because I think the size of the stack isn't really big from the point of view of the size of my computer. I think this is an old-fashioned thing that's built into Maple, but I've looked quite a lot and I cannot find a way of turning it off. So I'm using this little trick. Right. So this now works out of the box. I don't have to do something clever in order to compute big Fibonacci numbers, and then I run. So this is my Fibonacci 1b, which avoids the problem of filling up the stack by calling it sort of preventively at smaller numbers and actually just throwing out this information. And now I can do this pretty far. We're going to have to wait, but remember, we're not waiting more than 10 seconds. So this time I can get to 2 to the 18 before spending 10 seconds, which is quite a lot larger than what we had before. And you can see that the time that was spent to find Fibonacci 1b is very small. And now I see that actually I cheated a little bit because I had already run Fibonacci 1b. Okay, so of course when I had run Fibonacci 1b, I had filled out the remember table, so we should empty the remember table using forget. And now I go down again and run it once more. That was somewhat dishonest, not on purpose. So this time I don't think we get nearly as far. Okay, I do still get to 2 to the 18, but you can see that this time it cost me some time to get like 2 to the 10, 2 to the 11, and so on. I could also try Fibonacci 2, which is the one that uses the expression, the closed form expression that I have from theory of Fibonacci 2. The procedure here works the way that it makes the computation and it asks Mabel to simplify it. So that's not as fast as the direct thing that we did before, but it does give me 2 to the 14. And then I could do the same with Fibonacci 3, which is the one that uses the round-off method. And again, it gets me pretty far. All the way to 2 to the 22. And we can sort of see just by double checking these things, I get the same numbers at 18 as I get here and so on. So things actually work out. Now, we see that the time consumption by Fibonacci 2 and Fibonacci 3, it grows, it has a sort of a fairly straightforward growth. I would say that if you sort of plot it, it looks almost like it would be some sort of power law growth. But of course, you have to realize that I'm feeding Fibonacci bigger and bigger numbers. So the input is 2 to the 22, 2 to the 21, and so on. So the fact that I'm not seeing exponential growth means that my procedures here, except for the first one, are actually very fast. They work in exponential time, right? Because even though I feed it input that grows exponentially, the time consumption does not grow exponentially. So that's what's going on. And by the way, returning to the definitions of my Fibonacci 2 and Fibonacci 3 here, you see that these are actually closed form expressions. Right? There's nothing in this, there's no loops, there's no repetition, but of course there has to be some computation going on behind the scenes because we're asking Maple to simplify these expressions that get more and more complicated. So of course this is not something that we can see directly, but what's going to have to happen is that Maple computes this number and then spends some energy finding the integer that you get by simplifying the expression. Or down here, what Maple needs to do here is to compute this number accurately enough so that it can round it off correctly. Right? So there's something going on here that even though this is like a one-line thing that has no loop built into it, so you might sort of hope that it worked in constant time, that's not going to happen because we have to have more and more precision in order to get these numbers computed correctly.